Okay, hello and welcome to the CodeFlow video for the Drone Lab PC, the Intelligent Drones Lab. I gave you a separate video on the overview of the Copilot and how important that Copilot is, generally speaking, and why you would have to juggle multiple types of libraries in order to experiment on the space. So while this is not a video for the demos, this is a video for the experimentation, and so we'll examine the code base more closely. So let's jump right into it. If we go into our home, Drone Lab, our main folder is Crazy Swarm, which I'll open in, not in a new window, but in a new code window. Oh, there we go. And the folder contents looks like this. There's quite a lot going on in here. To simplify things, this is a workspace, a ROS workspace, and really everything is happening within this workspace. Other things here have been installation instructions for the Crazy Swarm framework. Once we're inside, we definitely will look at source files. I'm not going to go into depth into why these exist. If you're familiar with ROS, this should be a breeze. Crazy Swarm. Crazy Swarm is from which I have built my scripts, my actions, my launch files. So Crazy Swarm is the file. We don't have to look into source at this point. I'll be looking with you at the scripts, the launch files, and the action files. So outside Crazy Swarm are a few other functionalities used for the Crazy Swarm low-level firmware. Actually, it is the Crazy Fly low-level. So this is really the Python API around which we wrap Crazy Swarm more generally. This is exactly how Crazy Swarm came to be. As a ROS framework, they wrapped the different APIs, so moving to waypoints, etc., landing into ROS type messages. They are standard templates for ROS messages, and that's it. But first we need an overview. At the moment, our active demos are here. Inactive demos are actually archived content, and basically in the scripts file we will have these demos. We will also have essential backend files like the ROS action server. The code flow from the moment you create a message for a particular purpose to, so let's say from the moment you create a message that is supposed to determine a waypoint, to the use of that message within a server backend file, to the fact that that server function, which is an action, is loaded on a server, an active server, and then gets activated by the state machine. Let me go through all those steps now quite concretely. Let's say we look at our actions, and we have quite a few over here. At the moment, 2 are used, myNew and doTraj. If we look at doTrajectory, this one's mostly used for trajectories that are already generated CSV type trajectories, and you see that it takes a goal, it takes a result, and it takes a feedback. Now remember, this is what an action does. ROS actions will, once they're on the server, to activate them we will require to give them a goal. While they're activated, feedback is given as frequently as we decide it to be, and then finally when it's complete, these are the complete information. Let's look at the waypoint. The waypoint is not much different from DVIC. As you see, the waypoint has a specific point. Now you might ask what this is. A quick Google search, you will find that ROS has specific structures of messages. In this case, this point is composed of a point X, point Y. It's a point dot X, point dot Y, point dot Z, giving us a, not an array, but a ROS message. Alright. Once you've understood this, these messages that we decide on are compiled. In fact, they're compiled alongside the Crazy Swarm firmware, the other messages that the beginners of the Crazy Swarm framework actually put together. You can see that they all come together in the make lists file, where I have added mine and Wolfgang Honig added his service files, messages files, etc. Right. I had added some service files, he added other service files, etc. So let's take, as we said, this message and see how it is activated from within the action server. Now this is the action server. The action server is activated itself. It's launched with a launch file. Here we go. So in the demo that I showed you earlier, we would launch this launch file, which would take from the action server and take each function and turn it into an active action, into an active server action. So let's look at the server. There's a lot of initialization, a lot of ROS messages that are structured. Eventually, we initialize an action with its feedback, its result. And remember, the goal itself isn't initialized here, but it is received by the callback. So as you see, the CSV trajectory has a callback. It gathers this goal and it is able to use the ID of the specific crazy fly, and that's why we have an ID in our goal. And it is also able to utilize the shape that we want. In this case, the trajectory will be a helicoidal or a figure of 8, depending on the message. So now that you've understood a general view of the action server, and you see how we launch them one by one, you might ask, why are we launching so many? Well, each action, to be safe, one action needs to be attributed at a time. And if you have 5 drones, or 6 in this case, they cannot all use the same action to land. These are singular threads, and so we need to make one for each drone. And I had a land for each drone, I have a trajectory for each drone, and a waypoint. In this case, as you can see, the trajectory, which is called here. These params over here are CSV files. They are saved, if I'm correct, right here. Over here, we have a CSV file, and they are loaded, they are actually loaded right here into a parameter server. Not an action server, but a server that's more designed for constant values. They're received here, and then our ROS action server gathers them one by one right here. Alright, so I have put them in each different action just in case. I think it could be simplified, but that's how you would do it. Alright, once we've talked about the entirety of an action on the server, we can now look at how we activate it. Because while this action server.py is activated by the launch file, it is not actually started until a state machine starts it. This is where you go into the script file, into any of the active demos, and let's look at a trajectory in the active demos. Here we go. This active demo will activate one of these launch file functions. So let me show you what it looks like when they're active on the server. It is actually quite simple. All you would have to do is go into the right folder and ROS launch the server. That activates all our action folders, action functions really. It also gives us a preparation for the state machine, which we would launch afterwards. But I want to show you that these are in fact active, all of these. And if I show you in a different window what is active and what is not, here we have ROS topic list, which shows us this. Just give me a minute. Let's activate the entirety. It seems ROS topic list does not show us our actions unless we start Crazy Swarm, and then Crazy Swarm gives us this list of actions, of topics rather, sorry. These topics give us direct information on command velocity, logs, pose. But when we launch our action server, we have all the different goal, feedback, result, status, cancel. I encourage you strongly to look into what all of these do. We were talking about how these, once they are active on the server, will be activated by one of our state machines, which is this demo CSV trajectory. This state machine starts with a set of points, which we've tailored to the demo, but it quickly starts with activating a smash state machine. Now smash is a Python library. What's very cool about it is it gives us out-of-the-box functionality. It is a little finicky, so I would strongly encourage you to practice with the turtle simulation before you try it on drones. I have a little course that I've put together on that subject, and that one of the students of the DVIC did follow, and leading from that course we were able to create a choreography. In this case, Smash helps us to call each action by name. Recall that the names of the different actions were in front of us. As you remember, our actions were activated by name here. Waypoint, draw an X, trajectory, draw an X, see, here. And then in the goal, we put in information. Now we have to go back to where we started, information that I showed you in the messages. So remember that a message has these goals. In this case, we have a my new action as here. It needs a point, an ID, and a shape. As you see, it does not have a shape, so arguments are not enforced. But once you have that, you can also give a transition from each state to another state. I'm not going to go into detail on how this works, but Smash helps us actually have concurrences, preemption systems. If you look at how Smash is coded, it is coded in Python, and it is very clear and transparent how they do each state of each action. As you see here, shapes are helicoidal, and they can be changed to figure of 8. But this is the main demo. We won't change anything. I would encourage you to keep these demos identical and experiment somewhere else. Alright, the state machine has a landing clause with concurrences, etc. You've seen it in the demo. The state machine has a visual aspect as well, and that is the introspection server. The preempt handler is important for Control-CN and preempting essentially the state machine in case of accidents. Right. Once I've explained this to you, there is not much more to explain. We can add different velocities to the drones, and then we can go back up this CodeFlow to be able to integrate it into the main functions. For example, you add a velocity here, you build the Rust file every time that you change the message with a cat can make, and this will then be able to be activated on something like a trajectory callbacks, where we wouldn't have just shape but also velocity. It's a good example of where shape would affect this. We can add different arguments to an action. Let's say velocity over here, and then in the Rust action server, in the callback, in each callback, where we're using this particular message, we could use it to affect the Python API. So just like here, I used it to affect the shape, you can use velocity to affect the timescale, basically. Alright. Reading through this callback, you see that it needs to have a completion system. Each completion requires a flag. I've made sure that each action that we have in the demo does complete, which is very important. It does allow preemption, which is incredibly important. In this case, I had to cut down the trajectory sleep time so that there were opportunities to preempt. But in other times, you can preempt directly. And finally, there is the possibility for demos to land properly. Let's talk about demos that land properly. At the end of a state machine, there is a land end to make sure that drones land properly. If you have a transition to another state that's already inside the state machine, this will go on indefinitely. I did this for a demo I did today, but ideally I'd want to finalize it with an outcome of the entire state machine, which ends the demo. So just something to remember. Something else to remember. Now, while all this was abstract and it was software, sorry, not abstract, but it was a software exploration of the system, we have to link it somewhat to the real hardware drones. You've seen in the demos how I've done it. I think an essential part of the demos, which I think I didn't mention back then, but I need to say, is that each demo script identifies the IDs of the drones that are in use. Drone 2, and this is the actual ID 2 of the drone, this is the actual ID 3 of CF3. If you choose to use other drones, you will have to change these because they are called upon in the script multiple times. See, you can see CF2 and CF3 are called multiple times. Crazy Flat 2 and Crazy Flat 3. Alright, so having said that, there might be one thing to add, which is how do we generate trajectories in the first place. Demo 1 is generating it from a CSV trajectory. I think I'll link it below, but it's a lovely library to generate a trajectory from Bezier curves. I think you can explore all sorts of trajectories you can create yourself, but this library is from the creator of Crazy Swarm. And then the other demo that we have moves between separate points, and so these points are given to the drones and the drones fulfill them one by one. And that's about it. Let me quickly check if I have it all. Okay, 2 questions I've had from my audience is that the question is how many drones can we fly at a time? On the original Crazy Swarm framework, we are limited by the antenna, and so I've read that they have been capable of flying 30 drones through 3 antennas simultaneously, so about 10 drones per antenna. My experience with the lighthouses and our current system is much lower. I think having 2 lighthouses is extremely limiting. We need 4. That has to be done. But once we've said that about Crazy Swarm, how many drones can we fly using this copilot that I've designed, this action server? Well, in theory, as many as possible. I've put in 6 over here. So technically, there is the possibility for a synchronicity of intelligent behavior. I'll just put it like that. Another question. Are you able to use Crazy Swarm and Python API on their own without this copilot? Yes, you are. You are able to activate Crazy Swarm and then use it to pilot each drone using the Python API. Again, This, in my opinion, defeats the point of intelligent behavior. Intelligent swarm behavior and swarm robotics at large will require each drone to function independently in more complex situations than just using the Python API. Let me rephrase. Yes, so you can essentially rebuild another Copilot, but I hope this one is clear enough for everyone to use. Great. Of course, it's a robust Copilot, and today I've filmed 2 videos, one moving between waypoints indefinitely until the battery was out of energy, and the other video which was the drone performing a trajectory, landing and starting again indefinitely. These are possible because of the state machines. Alright, thank you, good luck.